Log on, tune in, find out. Another good idea from Cambridge.
About the linear Boltzmann equations and Dirichlet series. Good. Switch on the microphone now. Switch on.
Okay. No, maybe. Okay, I will find the level. So first of all, I would like, of course, to thank organizers for inviting me here. So nice place, and I'm very happy to see many old friends and new people here. So this is my talk is a sort of opposite kind of talk compare with typing you. I will speak about quite small and technical problem, which nevertheless looks to me interesting. And this talk is based on a joint paper with Irene Gamba. Here is the plan of the talk. So I will make introduction, mainly devoted to motivation and main goal of explain main goal of the paper. Then most of or half of the talk I will speak about linear Boltzmann equation in a very simple version, how to solve it. And then the main part of my talk will be about connection with the Dirichlet series, and so it is a bit strange subject because most of my life I try to apply mathematics to some physical problems. Here is something different. I try to apply kinetic theory to pure mathematics. So to study, I remind you what is a Dirichlet series for those of who do not remember. Yes. So it is a series u of s equals sum of a n divided by n. Sorry, it must be up, of course, to the power s. Yes, when s is a complex number, and of course the most famous Dirichlet series is the Riemann zeta function. So this is what I'm going to speak about. So now we start with this introduction. I remind you some elementary facts you know very well about classical special functions. So roughly speaking, all classical special functions can be divided on two groups. And the first group, which is used a lot in mathematical physics, are spherical and cylindrical functions, various orthogonal polynomials like Hermite and Laguerre, whatever. Yes, and second group, also we use it a lot, like gamma function, beta function. Riemann zeta function belongs to the same group, and various generalizations of Riemann zeta functions, for example, polylogarithm, which is denoted by Liz of x, and it is simply the sum xn divided by n to the power z. So what the question for students is who are familiar enough with this stuff is what is the main difference between these two groups, and the answer is that functions of the first group are directly related, are solutions in fact of certain ODEs or PDEs. We'll say we know that ODEs sometimes through PDEs, I mean that spherical and cylindrical functions are related with to Laplace equation, and then the separation of variables in spherical or cylindrical coordinate system. But functions of the second group are quite different. And Hilbert, in the beginning of the century, of the last century, of course, conjectured that zeta functions and function and other functions of similar type do not satisfy any algebraic differential relation. So it cannot be any ODE or PDE which are for which these functions are solutions. And his conjectures were later proved. Just to give references to Mordechai Bolovskoy in 1914, Ostrovsky 20, and a lot of other reference, and more or less discussion of this problem can be found in the book of Karasuba and Voronin. So this means that a connection between, say, polylogarithm and zeta function to solutions, connection with the solutions of some equation will be an interesting fact. And our goal is show that this connection surprisingly exists, and this is connection to our Boltzmann equation. This is very local problem, fact, and this is just an observation. I don't know how to use it, and I will tell you about difficulties, but still, this is hopefully you can use it better, you can find the use of this better than me. My job is just to tell you about this connection. So, okay, now we speak about linear Boltzmann equation, which I mean. In this case, it is the linear Boltzmann equation for Maxwell type of interactions. And the simplest version, without special dependence, I don't need it. So I have a distribution function f of vc, and v is of course velocity. I consider 3D case. It is more convenient, so there is no big difference. But also time is a positive number, and the linear collision integral means that physically this means that we have a test particle, and we consider a relaxation of this test particle in the equilibrium in the equilibrium gas. And for simplicity, it is enough for me. Mass of test particle is exactly the same as a mass of field particles. So we have, and g of cosine t is, as always, differential cross section multiplied by relative velocity. My notations are standard, so it is integral dw d omega, cross section, then usual brackets, and the m capital sub t is a Maxwellian with the temperature. Okay, so it is quite standard. I don't need to tell you something, and I will first explain you how to solve it. This was done in my work 30 years ago via Boltzmann, via Fourier transform, of course, is the most convenient way. So what we do, we make Fourier transform, then this leads to much simpler equation for function psi, which is psi is a Fourier transform of f divided by Fourier transform of Maxwellian. So Fourier transform of f is psi times Maxwellian. Then it is easy to see that we have equation which does not depend on temperature at all. This Maxwellian with this temperature, it disappeared from the picture. And we have it, of course, as always with Fourier, we lost three-dimensional integral. So we have a very nice equation, psi sub t equals integral over unit sphere. Again, this cross-section. And then psi of k plus modulus k omega. Omega is a unit vector divided by 2 and minus psi of k. Moreover, I will not need a general solution. It is possible to easily construct a general solution, but I will need just isotropic solutions of this equation. So isotropic means that my function f depends only on modulus v, then also phi depends on and psi depend on modulus k, and I denote x equals modulus k square. And now I want to consider a function which is psi of x and t. Both variables are positive, real variables, and I have equation psi sub t equals L psi, and now integral is looks very nice. It is integral 0 1 ds g of s. It is the same kernel g, but slightly modified. Psi of x minus psi of x, and the initial data. And my assumption on this function is that it is non-negative, and this integral must be bounded. This integral is the same as transport cross-section. So normally this function can have a singularity at s equals 1, which correspond to scattering angle equals 0. But the important thing that this singularity must not be too bad. This is the meaning of this condition. Okay. Now, how to solve this equation? Is very simple. I make a bit more convenient form for this equation by change of variables and introducing instead of previous s new variable tau under the integral sign. So I have integration d tau. Now I have a kernel k of tau, which relates to the previous one by simple formula, and I have psi of x e to minus tau minus psi of x here. Most important thing is as always, you consider the linear equation. You look for eigenfunctions of operator, and in this case it is very easy to see that eigenfunctions are x to any power p. It can be a real number too. But and then the correspond. It is simply you substitute here x to p, and you see it immediately. Yes, and eigen values are given by simple formula, the lambda of p integral 0 1 d tau k of tau 1 minus exponential minus p tau. So I even don't want to discuss in which space, etc. It's just it is formally. Yes, and then you can say you can introduce spaces and whatever. But what this means, you know, that if a distribution function was decaying fast enough at infinity, this means that Fourier transform will be a smooth function, and we can assume that in many cases Fourier transform can be written as a Taylor series in X. But then, if your initial data for this equation is given in the form of Taylor series, you immediately, by this formula, write the solution. Yes, and what is important, that I didn't specify function k of tau, therefore it is blue here. This is correct for any k of tau, or just we need this integral to be finite. Okay? And on the other hand, you can ask, what if this representation does not work? What if I have a general function not infinitely differentiable? Then it is possible to construct integral representation. I just say a few words about it. That another form of solution of this equation is through some kernel, that psi of x and t is g tau kernel r of t tau, psi 0 of x exponential minus tau, where we have a explicit formula for r. It is inverse Laplace transform of the function lambda exponential of minus lambda of p t. To show this, the simplest way is to notice that actually the Boltzmann equation, here must be psi t, it must be derivative, sorry, is equals, you can write it in the form that this linear operator is in fact analytic function of a differential operator g dx. And this analytic function is a function like that. But then you can immediately solve it in this form, since analytic functions of the same differential operator, they for algebra, you can multiply them, etc. Yes, and then you will have integral representation immediately after that. So this is the simplest way, but I will not use it. I will tell you in advance that by using integral representation, I can construct many formulas, but they are most of them are not new. Now, I go to Dirichlet series as I promised you. So I remind you again that Dirichlet series are this series of the type that you have arbitrary coefficients n to minus s. Now, on the other hand, I can construct solutions of my Fourier transform Boltzmann equation in this form, where lambda depends on arbitrary function. So, to make a connection, it remains to note that if I take this function in the form k of tau equals exponential minus tau divided by tau, then my lambda will be lambda of p, which is here, will be log of p plus 1. And therefore, it is very easy to make this calculation. I made it, of course. Yes, and then x multiplied by this function will have a form b n minus 1 x to n divided by n to the power t. And I will have identity that if I take Bn here in the form Bn equals An plus 2, then simply psi of 1t will be identical to u of c, where u of c is this Dirichlet series. So it's a simple trick which shows that which allows to make a direct relation between Boltzmann equation and Dirichlet series. Now, so in sense, the main result, which I hope can be used one way or another in the theory of Dirichlet series, can be formulated in a very simple way, that a solution psi of xt of the problem psi sub t equals this operator with the kernel exponential minus tau divided by tau, and here is standard for Boltzmann psi of x e to minus tau minus psi of x, and initial data like 1 divided by 1 plus x is related to polylogarithm, which is this series, by simple formula that this series, which is polylogarithm of minus x, is equal to minus x psi of xt. The connection with the zeta function is given by formula psi of 1. So I put 1 here. You see, if I put minus 1 here, I have exactly zeta function. But if I put 1 here, I have something very close to the zeta function times some simple factor, and this factor is here, and so I have the identity psi of 1t equals 1 minus 2 to the power 1 minus t to the power minus 1 times zeta of t, and the proof is actually already sketched above, and to have this, I only need elementary identity that psi of t is this series with minus 1s divided by this factor. And this is well known. And now you can ask me, but what is the connection with the Boltzmann equation? It is not something not useful, but nevertheless interesting, just of curiosity. Which cross section I must take in Boltzmann equation, and which initial condition to get what I showed you. And this cross section is g of cosine theta. Remember, cosine theta is scattering angle between 0 and pi, is inverse power of 4 pi log 1 over cosine square theta over 2. And what is initial condition? Initial condition is a distribution, something like Yukawa potential, 1 over v modulus v exponential minus modulus v, and convoluted with Max value. So everything can be more or less presented just in the case t equals 0. Then this is delta function, and convolution is simply this function, nothing else. And note that it is a singular function. Yes, but singularity is exactly a type we need. If you consider behavior of this function near theta equals 0, which means cosine equals 1, mu equals 1, then it behaves like that, and therefore what I need is a transport cross section is bounded. So everything is okay is a bit even strange that it is a quite physical, typical physical model for sort of true Maxwell molecules. And now let me explain what are difficulties and what we obtain. Of course, I try to get something useful from this before I publish it. Yes, but it was not easy. But what sort of problems do we have if we want to apply this idea to typical problems for Dirichlet series? Let's consider a generalized Dirichlet series with x to n. Yes, then if we put this x equals 1, then we have a usual Dirichlet series. What is the result of the paper? It is shown that this function satisfies this integral differential equation, which is the Fourier transformed linear Boltzmann equation. Difficulty and we did it, say strictly speaking, for positive values of s. S is time here. But of course, if you have the equation where it is satisfied for positive value of s by analytic continuation, you can easily conclude that this is true for any complex values of s until everything, all this, both sides have certain meaning. So let us take a complex Z, complex S, and it is traditionally denoted S equals sigma plus IT for Dirichlet series. Yes. Then F1 of S is true. Phi 1 of S is a true usual Dirichlet series is just this function at the point when you take x equals 1. So if you fix typical problem for Dirichlet series is that we are interested what happens when we go along some vertical line. So S, real part S is a sigma, imaginary part is a T. So our traditional knowledge about Boltzmann, we know everything until we are here. Yeah. But most interesting problems in Dirichlet series are along vertical line. And if you see what does it mean, we fix sigma, and we denote phi of sigma plus itx is phi with upper index sigma. So sigma is just a parameter. But then we need to solve Boltzmann, this Fourier transformed Boltzmann equation with imaginary type. So in fact, the difference is like between Schrödinger equation and heat transfer equation. We can find a lot of interesting things here, but nobody knows, and nobody, to my knowledge, did such things. Yeah. But if we are able to understand what happens when what are properties of the Boltzmann equation along these vertical lines in a complex plane, then we can answer many questions, and in particular for zeta function, there is a famous Lindelöf conjecture, which is a consequence of the Riemann conjecture, that zeta of on the line sigma equals 1/2. Zeta behave is O of modulus T to the power epsilon for any positive epsilon. This means that it is not bounded along this line, but it is less than it can grow less than any power. In fact, of course, it doesn't grow; it oscillates. Yes, but the maximums are like that. And you can easily express this problem in terms of properties of Boltzmann equation with imaginary type. Yes, or so this is completely open, and I don't want to comment more on this, but at least we consider it as observation, and it can be useful. In fact, we planned to submit this paper as a short note to Journal of Statistical Physics, but Irene decided to send it first to Peter Sarnak, whom she simply knew for many years personally. And he was, we of course were very pleased that he expressed a lot of interest and asked this paper to give this paper for him, he communicated it to Forum Mathematics, saying that most mathematicians do not read Journal of Statistical Physics. Maybe it is better to do this way. So at least, yes, there is a non-empty set of people who are interested. Thank you very much. Good. Yeah.
Thanks very much. Are there any questions? Well, in my sort of quite simple mind, I always had the idea that the theta function is really quite complicated, and maybe linear Boltzmann should be at least be a bit simpler, because it's more familiar to me. Now you show us these links. Does it mean now that that linear Boltzmann is already really hard, or does it mean that the theta function should probably be a little bit easier than my mind thinks about it?
No, I think that no. We know linear Boltzmann for real positive values of time, yes. But if you consider time as a complex variable, it is as complicated as that, like that. At least, no, in some sense more, because more general. Just any Dirichlet series is a solution. Well, zeta is in a sense a very simple function, because if you like, write it in the form of integral. Okay, I can give you example. Where is the chocolate? Okay, so this is like something like zeta of c is some constant which does not matter. Okay, integral 0 infinity, say gx x to c minus 1 divided by exponential to x plus 1. It's a very simple integral. What is it? Yes. So if you forget about this plus 1, it will be just a gamma function, and you know everything about gamma function, yes. But if you put I was fascinated by this really some years ago. Then I started studying a bit because it looks really simple. So this famous Riemann hypothesis is to show that all zeros of this integral lie on the line real part t equals 1/2. That's it. Therefore, it doesn't look more complicated than Boltzmann equation. Okay. Yes, yes.
Just made a simple observation that when you write down this integral,
Uh-huh.
I mean, the gamma function,
Yes.
if you think about it, the denominator is the e to the x, right?
Yes.
And which is sort of Boltzmann if you change x to y squared something. But this one you can rearrange it into some sort of Bose-Einstein.
Yes, yes, yes. It's even polylogarithm is directly related to moments. There is an integral representation of polylogarithm, and it looks like a moment of Bose-Einstein function, of course. Yes, but you just want to say that Bose-Einstein is more complicated than Maxwell-Boltzmann, maybe, but it is, yeah, when we speak in physical terms, we always mean positive things, variables, blah, blah, blah. Yes, but here difficulty is in complex domain. Yeah.
Okay,
Yeah, please.
maybe another comment, I don't know if it's appropriate, but the Riemann zeta function,
Yeah.
it appears, you can also interpret that in the way Faddeev did it. Faddeev.
Faddeev, I'm not
It
familiar with
appears, if you look at the wave equation on the fundamental domain of the modular group, then you construct a scattering theory, which means an ODP, and then this, the pole of the scattering operator are related to the zero of the, which means there is some room in some sense.
No, I'm sure there is quite a big book by the guy whose name is Mikhail Lapidus, I believe.
Yeah.
And like in search for zeros of zeta function, and so he discussed several physical interpretations, physical problems related one way or another. I don't know, maybe it is Faddeev is completely different, but I just say that several, yeah, there are several relations, but at least I never heard about something like that, a connection to Boltzmann equation. And that's it.
No more questions. Maybe let's thank the two speakers of the day again.